Hello, everybody, and welcome to the UFS webinar. This webinar is hosted by the National Weather Service Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. My name is Alex, and I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments, suggestions, and if you have any recommendations for speakers that you'd like to present at this webinar, please email us your recommendations at ufs.modeling@noaa.gov, and we can take those considerations into account. Due to the high number of attendees, you'll be in listen-only mode for the event. You will not be able to unmute. If you have any questions now or during the event, please submit them on the Google document that I will be linking in the chat shortly. And the presentation will last around 30 to 45 minutes, followed by a 15-minute time for Q&A. So just make sure you keep your document, send out that document, and you can put your questions in there. So today's presentation is Model Infrastructure Development in the UFS Weather Model, presented by Jun Wang. Jun Wang has been in the Environmental Modeling Center since 2002, working on numerical modeling and system architecture development. He's developed the Atmosphere Ocean Coupler for NCEPS Climate Forecast Model version 2, and later worked out various Earth modeling systems, including Global Forecast Model, Whole Atmosphere, Space Weather Model, and Global Aerosol models in the UFS. Currently, she is a team lead and member developing the UFS Weather Model infrastructure to support operational implementations and the research community. So I'm going to pass it over to June to give her presentation.
Hi, Alex, just want to check you can see my slide. Sorry, can anybody hear me?
Yes, we can see your slide. Sorry, I was muted when I said that, but yes, we're good to go.
Okay, thank you. Good afternoon. My name is Jun Wang. It's my great honor to represent the whole development team here to present the work. As you see, the major contributors are listed here. I'm sure there are more doing some work to help develop the model infrastructure team. This is not one person or one team. The work has been conducted through collaboration from many teams. This includes the NOAA centers and laboratories, including EMC, PSL, GSL, GFDL, OIR, and also ESMF team, Unidata team, the CDF team, MCA team, DTC team, EPIC, and NASA team, and some team from GCSPA. This is a community effort. We're trying to build a foundation for the UFS weather model to support both operation and the community development. Here is an overview of this talk. First, I will talk about the fully coupled capability, and then the build system, UFS weather model computational performance, the open source and open development strategy for UFS weather model infrastructure development. Then present work and planned work, and some I will leave some key points for you to take. So in the past several years, when we developed the UFS weather model, we go from a single component to the fully coupled Earth modeling system. This capability is developed through the open source software development. It's supporting both research and operational implementations. On the right, you see the code structure. Currently, the UFS weather model contains 17 authoritative repositories. It has 9 major flagship model components It uses the community mediator and 9 shareable UFS caps. As you see on the right, we have a UFS driver, and all the other components are yellow. Basically, they are the UFS component with the UFS cap, and in the center is the community mediator. This model actually was designed and developed to support as a foundation to build a unified system. The application I listed here, including the coupled model prototypes and operational pre-implementations, including GFS version 17, GAPS version 13, regional model, ROOPS version 1, air quality model version 7, hurricane model HAPS version 1, and also we're exploring the FB3 JEDI connections, and also support the marine DA forecast system. This is the same code base and support all those different applications. Here I listed a major achievement from each component. Here, the first ceps, which is a community mediator. It is the centerpiece of the whole coupled system. It is community developed and feature rich and easy extendable. For every 3 ATM, there are lots of effort put into develop the atmosphere model. Some major updates here, develop a completely new FB3 atmosphere UFS cap and CCPP physics and asynchronized I/O and coupling capability. Then we updated to size 6 as a community size model and use MOM6, the community ocean model too. I will talk about the component achievement separately. So this is a summary of that. Next on the CMAC, which is Community Multi-Scale Air Quality Modeling System. It is used in the regional air quality model system. And then we also have the GO-CARD, the GADA chemistry aerosol radiation and transport model to support aerosol forecast. And we updated, developed a new VWatch3 UFS cap. It is mesh-based and it has the unstructured triangular mesh feature. And another one is on CDEP. It is model component. It brings a new feature to UFS. We'll talk about that later. Here is the CMAX, the community mediator. We used to have a in-house NEMS mediator in UFS, and later we transitioned to this community mediator. As you see, the benefit, first, all the latest ESM features has been adopted in CMAX through the community development, and it contains the diagnostic capability for a water and budget and energy budget. The mapping method in CMAX, there are many different methods can be used to reduce the cost. The CMAX mediator is community-based. It is community developed and tested. It helps ensure the robustness across multiple applications. So basically, the code is structured as a set of reusable modules, can be used in several different Earth modeling systems. So this way, it provides separation of concern, but also the code is interoperable. The figure here you see is when we transition from NEMS mediator to CMAX mediator. On the left, we have SST difference from NEMS forecast. It is a 2 rounds on 2 different platforms. The difference on the left, it is comparable to the right, which is the SST difference between CMAPs and NAMs. The results are verified and the transition is completed. Next, on the atmosphere side, currently UFS has FE3 ATM as its atmosphere model with FE3 dicore and CCPP. Here is a code structure. As you see, it is a complicated at this time. There are several major updates since FE3 dicore was selected as a dicore system through NGGP project. Since then, the previous GFS physics package was replaced by the CCPP framework and physics, so it can support many different physics package. And after that, we also have the asynchronized I/O supported. As you see here, left, the forecast grid component can run simultaneously with the write grid component on the right. And after that, we also developed the inline post, the UPP, on the write grid component. And the next step, when the hurricane application comes on, they have the multiple domain forecast. So the nested case, they have either static nested or moving nest. So this capability is integrated into FE3. So in that multiple grid, multiple domain application, we also have asynchronized I/O. When the forecast is going on, you will see all the products coming out along with that. Next, on the size 6, it is the community size sea ice model. One major achievement is we replaced size 5 to size 6 in UFS. The size 6 is released in 2018, and there is some code refactoring and modernization, and there is new ice physics package, and it is integrated into UFS. The validation was done. You can see the picture on the right. On the top is size 5, bottom is size 6. The results are comparable. So the both size 6 and size 5 perform similarly. One major achievement is the shared UFS cap is implemented when we transition to size 6. Next, on MOM6. MOM6 is a well-known community ocean model. The MOM6 UFS cap already exists for some time. Here for us, we updated the MOM6 cap to use the CMAPS mediated. Meanwhile, we also add several new features. One feature is this what we call the ocean lag method. It simplifies the cold start process. So we used to have 2 steps in order to run a cold start in the coupled configuration. And then with ocean lag, the atmosphere can send the required data to ocean and let it run at the second step. So the simplification actually help us save the time and the complexity. And the difference, as you see on the right figure, the 2-step cold start and the 1-step cold start, even after 12-hour forecast, the difference is really small. Another new feature is the a mesh option is added to MOM6 cap to use mesh in the coupled configuration. Here are 2 other components. One is the AQM, air quality model. It is a CMAC based. We developed a new AQM UFS cap and some other features, including the Fengsha wine-blown dust emission scheme. And we also enabled the scavenging and wet removal in atmosphere side. The regional configuration is enabled in UFS compared to operation. We have a big domain here in the colored domain you see. it covers the 3 separate domains we have in operation, which is the 3 small domains. And at this time, we're in the pre-implementation stage to implement the air quality model. On the right, you see the go-kart and atmosphere coupling. So there's a aerosol UFS cap was developed. As you may know, the go-kart components, they are all in a USMF component, but based on Maple. So we have the Maple infrastructure introduced into UFS, and on the top, we develop a new cap. Now, currently, it allows 2-way coupling for atmosphere and aerosol. The radiation impact can be considered. Next is on WaveWatch 3. We developed this mesh-based UFS cap. It utilizes a mesh instead in place of a grid in the cap. So mesh gives better structured, or mesh can be either structured or unstructured, making them more flexible. And also the new cap is coupled with ceps instead of direct ESMF connectors. This feature is critical to us because it provides restart reproducibility for WaveWatch 3 coupled applications. And it also allows flexible run sequence because the coupled field can be either instantaneous or accumulated in the ceps. This mesh-based cap accommodates the unstructured WaveWatch 3 meshes. So this also gives us some benefit. One is that it has significant advantage in scalability and coastal resolution. It helps give better resolution in the coastal area. Another one is that you can see on the right figure, it allows wave field to be continuous across Mount 6 triple theme. So you see on the top, it is the Mount 6 structure grid. It is 1 degree triple grid, and there is a blocker on the triple theme. And on the bottom, when you use the unstructured grid, you see the field is continuous. And I do want to mention the pole area is masked out. As you know, there's still singularity issue in the WaveWatch 3 when we use the PR3 scheme. Next, I want to introduce the ceps. It is Community Data Model for Earth Prediction System. This is a new model system, data model component. It is feature-rich and very easy to extend. Currently, we have data model for atmosphere, ocean, ice, wave, land components. And ceps, actually, all those data model, it reads external observation data or model output data at available time and resolution. And it can do interpolation in time and space. So it can basically send data to the components that require those data sets. It allows isolation of feedbacks between components. If you want to investigate the coupling feedback, you want to isolate one way coupling, you basically can replace with data model easily. And it also allows the capability to build the hierarchical testing for component models. Next, I will talk about the build system. I do want to add one sentence. So we are talking about the new CAP. The idea is to have the model component shareable and reusable by other components. This is a community. We know one component may be used by other system. So the way we build, we hope it can help engage more people when they're working on the system. Build system, as you see, the UFS weather model supports applications with various level of complexity, and it also supports operation and research community. So we used to use the GNU Make, which is very not easy friendly for user to use. And we transitioned this to the CMake build. CMake provides cross-platform support and also improve portability and require less maintenance. This is exactly what we need in the UFS infrastructure. So for each component, when we integrate the component into UFS, the CMake build capability is developed. So I think 2 years ago, all the UFS weather model was switched. The applications are switched from GNU Make to CMake build. Another thing I want to mention is we unified the UFS model code repository. For users who has been following with UFS weather model, you may know in the past we have several repositories like UFS weather model, UFS S2S, DATM repository. Each of them is one UFS application, but they are located in different repository and they use the same subcomponents. So in order to simplify that, we unified all those repository into one repository. That's what we see now, UFS weather model. So basically the same, it provides the same code base for all the applications we see at this time. This is a critical step for us to reduce the large number of operational models. Another thing, porting, as you see, build system is critical for porting. When you get the code on any platform, you want to have a simple build that you can create executable and you can run experiment. So we actually put some efforts to port the code to NOAA IND platform and other platforms like cloud or laptops and so on. This is to support the research community and universities. Another recent work is to adopt the spec stack library. It can help support multiple versions and configurations of library on a wide variety of platforms and environments. This is all to support the build, make the build system more user-friendly. Here is the current status of the build system. On the top, I listed some supported configurations, and there are some new here. Basically, it can support atmosphere only or atmosphere coupled with other components, and the configuration could be just depend on the combination of your components. And in the UFS build system, it can be very easy to specify a application you want to build the components together in a consistent way. On the table, basically, the first column, I listed some major configurations, and you see which components are connected in that configuration. I want to mention in this build system, a single executable, it can be compiled with several physics configurations, which we call the CCPP physics suite. So this way you can test the different physics package using the same executable in your experiment. Meanwhile, for testing purpose, all those executables can be built simultaneously with different configurations, including different components. Testing. So far, we made lots of effort build the regression test framework. We all know testing is critical if we want to maintain a high standard code quality. Develop a regression test framework. Here, the goal is to have this DevOps in UFS development. And the regression test we have been developed listed here, application test. So as you see, all the configurations you see in the previous page, each one of them will have a test to make sure the application is still working when there is a change coming into the code base. There is a resolution test to make sure the features, targeted features are working for those resolutions. We also have feature tests if there's an innovation, and we have procedure to how to get the innovation into the system and make sure it doesn't break other configurations. We also have some stability tests, and the code quality test, what we call, is very important. The idea is that we need to maintain a certain level of reproducibility. One person runs the test will get the same result as another person when they have the same environment. Even though some configuration could be different, if you are running with different MPI tasks, if you are running with threading, decomposition, if you run the code in the restart mode, you should get the same results. And we also have this mandatory debug test to make sure the code updates are reliable. I want to mention, Epic actually pick up this and continue working on developing the test framework. Here, I want to show you the achievement to develop UFS Weather Model to simplify the NCEP operational suite. Since UFS Weather Model is supporting operation and the research community, in operation level on the left, you see the models running on the operational platform. There are many, and the target is on the right side. So we will have less model, and we still support all the capability we have on the left. So the box in yellow are those configurations that are already in UFS. So we still have some models need to be integrated into UFS. Next, I will talk about the computational performance. The infrastructure team actually put lots of effort on the computational efficiency. As of today, we all know resources is critical. We need to run the model efficiently, especially in operation and in the research community. Several examples I listed here is to help run the UFS in an efficient way. One work has been done on VAR optimization. So this is a case. We originally, you see in the table, the first two row, when we triple the MPI task, you see the speed up is about only 6%. So we know this is not efficient. If you want to run the model fast, you thought if I give more tasks, it will do. It doesn't have to be. So the issue is identified, and some work has been done to remove efficient data collection and implement the threading. So the last two columns you see the speed up if you are running this with the same MPI task compared to original code, you got 18% improvement. And also when you triple the MPI task, you do got the about 60% of saving time. This is another work we have been done using data compression with parallelization in operations for those people who are running high resolution tests. You know the disk space is an issue. So when we start working on the UFS, one case we found is that with C768 127 levels, it's about 13 kilometer runs, and original data is about, the binary data is about 34 GB. So for us in operation, we run 4 cycles, and the total data would be for 1 day would be 7 TB data. And write out each of these files will take 80 seconds. And we were looking into transition to a community standard NetGL file without compression. We got running time. Writing time is really big. So we compressed the data. We applied the parallel writing, and in the end, as you see, the data size was saved about 80%. And also the running time actually speed up. It's about less than half time. So one thing I do want to mention is for GFS version 16, without this feature, and it cannot be implemented. And also this work is collaborated with Unidata and PSL. And this is an effort from the community to help operation. Another feature I want to mention is Inline Post. Basically, one thing I do want to point out is that using Inline Post compared to what we call offline post, you save not only save the time you need to read in the input data, it actually reduces the pressure in the system, the I/O pressure in the system. So as you see here, to produce the same results, the inline post only takes 39 seconds, but offline post, it takes 211 seconds. So when you reduce the I/O, you allow other people to use the I/O capability. Inline post capability has been extended to multi-grid and moving nest. This is actually what we do for all the applications, and it is used. The multi-domain moving nest has been verified in half application. This is EN forecast. As you see, when models doing forecast, you see the post results coming out. Next, improving data transfer between the forecast and I/O server. As you see, we were using asynchronized I/O. So basically, the data will be transferred from forecast side to the right grid component side. So the transfer time is critical. So I want to highlight this slide because ESMF group, when we let them know the issue, we found the slowness. For example, every transfer, of course, the data about 40 GB data, every transfer, it takes about 4.5 seconds. And we need to reduce that down. And they actually did some development work and save 85% improvement of communication time. So with that data set, it eventually gets to 0.5 seconds for the transfer. We have been constantly monitoring the coupled system load balance. As you see, if you are running an experiment without load balance or run the model in an efficient way, you need lots of resources. And it doesn't guarantee you will get faster turnout time. And so for this, there are some work has been done to identify the scalability issue in the code updates. As you see, people are making science or technical updates all the time. We commit the code into the UFS weather model, but we do want to check if there's anything can impact the scalability to basically everyone that use the model code will get slower runtime. And we monitor the load balance in the coupled system. and monitoring the resource efficiency. So basically, every PR when it comes out, we are monitoring the memory usage, the runtime usage, even though it doesn't fully cover all the experiment configurations, but we want to at least have a sanity check to make sure this is taken care of. Some other code optimization. We have been developed this mixed mode data type in UFS coupled application. For those people who may not know this, basically we run die core in the 32-bit. It runs faster, and this capability is available in when GFDL delivers the FE3 die core. When we run that in the coupled mode, because FE3 and MOM6, they share the same framework, FMS, so that doesn't allow us to run one is 32. MOM6 has to be 64. So thanks to GFDL, and they made the updates in FMS, so it allows us to run in that mode in coupled system. As you see, we see the saving time for 25-kilometer application and 13-kilometer application is about 20%. Other updates on use the resources efficiently. We are using the new feature ESMF group developed. It's called ESMF Managed Threading, and it helps us help us use the resources efficiently. So the cumulative performance gain is 12%. And we are also explore other compiler options to speed up the model, and also we still maintain the reproducibility and all the other features. Next, I will talk about the open source and open development with the community. This is an example I want to show you how the collaboration of 4 organizations makes a moving nest capability in UFS. So GFDL, they developed this parent and telescope nest, this feature, and then AOML, they developed this moving nest feature here. And when then EMC and NCA, we developed this asynchronous I/O feature. So basically, when you have moving nest, you have post products coming out along with that. Of course, that including the history files and so on. So with this collaboration, we have this new capability, and that can be used in operation. The open source and open development with community is critical. We do want to engage the community involved. The UFS Weather Model is public, and it is on the GitHub. The URL is here. Currently, we have 200 folks and 140 active developers. And so far, we have more than 1,800 issues and pull requests resolved. There are 10K files and 4.3 million lines of code. On the right, you see the basically the code update. We get the history from UFS Weather Model. Each node you see here is a repository, and the flash or the light you see is the commit we made. And you see every time when there is a new star climb form, that's when a new component is added, and you see lots of flash. That is sometimes we have big commits coming in. So the involvement and the from the community can be shown in this figure. The idea here, we want to support operation and research community, and we want to closely collaborate with the entities in the UFS community. Okay, I will go forward with that. Present and planned work. Those are the list of the current work. I may not go every one of them. You can see basically, we want to improve the coupling capability further. That includes exchange grid or couple with new component and add the new coupling capability. And one thing I do want to mention is we want to set up this hierarchical testing. We will apply new data compression algorithm to further improve the I/O. In general, we know the I/O is a bottleneck in the system. One thing I do want to mention, we have transitioned the code management, R&D platform support, user support to Epic. We'll continue closely working with them, especially support operational platforms. We are working with Epic and other teams to develop this hierarchical testing. The testing is critical. Some other work, including jointly with GCSDA, implement JEDI in UFS. Another work may come is integrate the new die-core MPath to UFS Weather Model, and we have been still supporting operational implementations. Key point for you to take away. There are at least 4 key points. First, I want to let you know UFS Weather Model is built consistently. It supports various configurations and support previous and upcoming operational models. So operation model in the future comes from UFS Weather Model. Second, we're still developing the coupling infrastructure to enable it the fully coupled system. Third, a significant effort has been put into improve UFS Weather Model computational performance. Last, UFS Weather Model is open source and developed through collaborations with the community. It is a community's effort to make the UFS Weather Model what it is today. Thank you all. Any questions?
Thank you, June. I'm going to change it over to the Google document so everyone can see that. Perfect. Are you able to see the questions document?
Sorry, I cannot.
I just put the questions document in the chat again, and then I'm also sharing it from my screen. If there are no questions, we'll give a few minutes. Are you still unable to see the questions, June? Because I can just read them off to you.
Okay, I can see it. So the first question, can you talk about the plan for UFS Weather Model to support GPU computing? First of all, I do want to let you know that there are several work have been done in the atmosphere side. That is what I know. Of course, there are other projects too, I'm sure. On the GFDL, they were looking into the F3 die-core to run that in GPU. And also in the CCPP physics, we see people making the code updates to run the CCPP physics with open ACC. So those are coming, but I do not have a timeline on when we can run it in GPU yet. I see the second question. Thank you. Do you have a comparison of the results 32-bit versus 64-bit for the C768 127 level quarter degree? Would this be operationally variable? Yeah, we do have some testing. I think both GFS version 17 team and the version GAPS version 13 team, they are using this feature. So there are people doing verification on this. My understanding is that this feature is currently used or included in the GFS version 17, which is the configuration you mentioned here, C768 127 levels and quarter degree ocean ice. Next question is the names IO write out parallelized. Before we do have this named IO, it is a customized IO package. It can write out data in parallel. So it is using actually MPI 2 IO parallelization in it. So the second question is the inline post using Unipost? Yes, inline post is using UPP, so it is unified the post system. The next question, what are we missing in the NetCDF lossy compression field compared to the original field? So there are some experiments has been done, as you see in the table it listed. I think it is the physics group. They have been looking into all the field if we output without lossy compression and with lossy compression. I think it's more than just one case. They actually run a certain period and then compare the results using the scorecard. My understanding is the verification showed that because when you compress, you actually lose the last several digits in the results, just like when you run 32-bit and run 64-bit. If you consider conservation, then it might not be as good with lossless compression, but in general, it doesn't impact the results. That's why we adopt that. One point though I want to mention, because of this inline post capability, yeah, inline post process data without lossy compression. So inline post use original model data from the forecast side. So if you want to have, you can use the inline post result it provides if you have some concern about the precision.
We'll give it just another minute to see if anybody else has any last minute questions, and then we can wrap up.
Okay, thank you. The last question. Can you visualize how the collaboration with Epic would evolve with your group in the next few years, in addition to the current collaboration, and how should we maximize the efforts? Okay, basically, I think I'm not in a position to represent the whole development team, but I do have can provide some personal insights on this. In general, I do expect Epic play a bigger role, especially connecting the community. Definitely, they did amazing work there. In the early age of the UFS infrastructure development, actually, we were spread too thin to support user. I think those are definitely, we expect Epic will play an important role to engage all the communities in it. User support, platform support. Another thing I do want to mention is new innovations. I know Epic has been working on, for example, bring cloud and new technology. For example, also build the CI/CD. Those are the new things they can bring in. In my mind, the team we have been working with from EMC, other research NOAA labs or communities, we may focusing, say, on the part we look, for example, the code optimization. If we work on that, my understanding, we will be part of a community, just like Epic. So if we have some insight on something, definitely we will work on that. Of course, we can share knowledge with Epic, but Epic will leading the roles in user support, platform support, integrate innovations into the system, and so on. That is my personal opinion. I'm not sure if that is even correct or not.
Great. Thank you so much, June, for giving me that talk, and then thank you everyone for that very useful discussion. So you'll see the link down at the bottom of this document to send us some speaker recommendations, and then also to subscribe for our future webinars. Thanks everyone for coming.
Thank you.